So last week we have looked at chapter 2 already. So I think we have learned the fundamental language, fundamental design and modeling. How many design modeling that we can use in order to model the circuit or to represent the circuit in Verilog. So we have 3. Remember that that is very important. All right. So you always need to use one of the 3 or all of the modeling style in your code later on. All right. Sometimes you need the data flow modeling. Sometimes you need the behavioral modeling, and sometimes you need the structural modeling. Depend on what kind of circuit that you design, and also depend on your experience. Yeah, and also depend on the constraint that you have. For example, if the design is quite complicated, quite big, all right, so you cannot go for data flow modeling or structural modeling, so you need to design using behavioral. All right, and after you get the sub module, the design for the sub module, and you want to integrate all the module together, then you need the structural modeling. All right, or sometimes you need to combine all the 3 modeling in your code. For example, you want to have the or to connect the signals, right? So you need to use data flow modeling, or you want to just model a simple gate, all right? So you can use data flow modeling, all right? And some part you may have quite very big or many inputs, all right, and many outputs, and you know what is the um, process inside your module, right? If you give this input and you know what kind of output that you want, so you can use the behavior modeling, all right, behavioral modeling. Okay, so it's depend on you, and you need to know all of the modeling style. All right, not too many, only 3, right? And the last one that we learned last week is this, right? Synthesis of design. So synthesis means converting the Verilog code, all right, to the netlist, to the circuit. Okay, that is design synthesis. And the last one we will see today, all right, we will look at this hierarchical design methodology. All right, so you have been introduced to hierarchical design methodology, the definition in chapter 1. So here we will see how we do that. Means that we have our sub module, and we want to combine that module to create a bigger module or bigger circuit. All right, so that is the hierarchical design methodology. Okay, so let's go to synthesis of design. I think here we have a step of synthesis. So there are 3 steps. The first one is inference. Inference is by replacing or converting the HDL code to the structural model. So this is what the quarters 2 do when you click the analysis and synthesis button. All right, it will give you the structural model or netlist of your circuit, right? And it will be converted to the what we call primitive gate. For example, you describe the AND gate, right? So it will give you AND gate, all right, or technology modules. Optimization, this one done by the software also to reduce the area. So the software will try to minimize your design as much as possible. All right, and try to improve the speed of the design and so on. And the last one is technology mapping. So this one is when you select your device. What if is the FPGA device that you want to use? So it will map to that respective FPGA chip. All right. So there are many FPGA devices out there. So when you select the target FPGA chip that you want to use, so the software will map your design to that specific FPGA device. All right. So now we will learn a little bit how the synthesis tools, in our case is the Quartus 2, inferent or convert the HDL code to the circuit. All right. Why you need to know this? Because when you know this, you will be a good designer. All right. Because you know exactly when you write the code this way, all right, it will be synthesized to this specific circuit. All right. That is the difference when you don't know what you write, the code that you write, you don't know, you're not really sure what the software will or the code will be synthesized to. All right. So it will make your circuit better in terms of performance and yeah, in terms of cost and everything. Yeah. So that's why you need to learn this. Although it is done by the hardware, but you as a designer need to know your code that you have, you design. All right, is it synthesized into what kind of circuit? All right. So last week we have learned data flow modeling is all right, synthesis of simple expression in data flow code. Data flow modeling is very easy, all right, to predict what is the circuit that to be synthesized to, because it is exactly based on the equation that you use. All right, so it's quite straightforward, except that one thing that you need to know. All right, this is the operator C. C is the signal. CAB is the signal. Can be any kind of character. All right. C question mark A and B. So what is this? This actually the code that will be synthesized to a multiplexer. All right. So this means something like this. Well, maybe I use this so that okay. Okay. All right, I try to use this so that I can write something on the slide. Okay, so if we use CAB, this means that the code is right like this. For example, we write something like this. sine C, oh not C, sorry, F is the output, F equal to C question mark A B. What is that? Okay, what is this mean? So this definitely use the data flow modeling, right? Because you use assign keyword. This is data flow modeling. Yeah. And when you use this statement, all right, the Verilog compiler, or in our case is the Quarters 2, will synthesize this code to a multiplexer. So it will give you this. Yeah. It will give you a multiplexer. Okay, this is the multiplexer symbol, right? So in this case, you have 2-to-1 multiplexer. So you have A and B, and whenever C, okay, C will be the select signal. All right, whenever C equal to 1, and F will be equal to, all right, if C equal to 1, F will be equal to A. When C equal to 0, F will be equal to B. Yeah. All right. Hope you get the idea. Okay. So so whenever you get this, you write this statement, so you will get the multiplexer. Okay. Here is another example. All right. And before that, inference of arithmetic operator. All right. So you can infer. You can infer the arithmetic circuit. For example, the adder, the subtractor, the multiplier, and the divider by using this character, right? So for adder, when you write plus, okay. So again, when you write plus in your code, for example, F equal to A plus B, so this is not O, this is not O, all right, not an OR gate, but this is adder A plus B, A plus B, all right, means that you want to have A add B, all right, not A or B. When you use this, this is A minus B, and the multiplication is not, oh, sorry, I need to show this. Yeah, so this is adder, this is adder, this is subtractor, right? And this is not the multiplication multiply, not the multiply symbol. Multiply, you need to use the star, so this one is actually star. And for divide, division is used the slash. the slash. Okay. So now let's look at the code here in this example. Okay. So let's see this. Right. So you have a module. The name of the module is mark at. All right. And you have the port list X, A, B, C, D. All right. Input is A, B, C, and the input is 16-bit in this case. All right. So this is how we declare our bit in size. The input that is big in size. All right. In more than 1 bit. For example, this is 16-bit, means that A is you have bit number 0 to bit number 15. B also the same, bit number 0 to bit number 15. C is also 16-bit. All right. Input wire D. This one you please in your code remove the wire here. All right. This is wrong. Please remove the wire here. Okay. Oh, sorry, not that one. This D. So the D is just an input, not wire. All right. D. And this is 1 bit. Yeah. If you don't have any square bracket and number like this, vector like this, we call it vector. So means that D is 1 bit now. All right. And output wire, this one also remove. Okay. No wire. Output X, and the output X here is also 16-bit. Yeah. And wire T. Now T is wire. Why wire? Because T is the internal wire between this module and this module. All right. That's why we declare T as wire, and the size is 16-bit also. All right. So here we see when we assign T equal to D, and here is question mark or select B or C, right? So we will get the multiplexer, all right, where B and C is the input, and D is the select, and the output is T. All right, and of course, what is inside here is when D equal to 1, so the output equal to B, and when D equal to 0, the output is equal to C, or T equal to C. How do we know that? How do we know what is in when D is 1, T equal to B? So look at the code. Look at the code. So here, when you put the first signal, and then colon and the second signal, so means that this one is if D equal to 1. All right, this one if D equal to 1. Oops, sorry. All right, so here when D equal to 1, and here when D equal to 0, exactly. Okay, and another one is you assign X equal to A plus T. So means that X, the output X is equal to A plus T, and this plus is actually an adder. We will learn adder in next chapter. But I believe that you has been introduced to adder in your previous course, digital electronic or from diploma, right? So adder is simply a circuit that can add number. So you have to input, here you add, and you have the result at x. So when you use plus symbol, plus character in your Verilog code, this means add, adder. All right. So meaning that the this Verilog code is synthesized into this circuit, all right, where this line of code will infer the multiplexer, and this line of code will infer the adder, all right, and the connection is this, based on what you have here. All right, so that is what we call synthesize. So when you write the code, you should know exactly that your code will be translated to this circuit, or will be synthesized to this circuit. All right. Okay, so let's go a little bit here. So this one, I think we have discussed last week, when we synthesize behavioral modeling. We have behavioral code. So you need to be very careful, all right, especially when you use if-else statement. So when you use if A equal to 1, B equal to this, else C equal to this, for example. All right. So if you use if, you need to have else. All right. If not, it will not be synthesized to combinational circuit. It will be synthesized to sequential circuit instead, which involve the memory element. All right. So for example, I give you an example. Example, you write the code like this. Maybe I use. Okay. For example, you write the code like this. Yeah, in always block. Hold on. All right. So for example, you in always block, you have always A, B, C. All right. You write if A equal to 1, maybe no need C here. Okay, to input enough. F equal to B. All right, and done. All right, you write only if A equal to 1, but you didn't write, or you didn't state what if A equal to 0. All right, so this can be synthesized actually, but it will not synthesize into a combinational circuit. This will be synthesized into a sequential circuit. We will learn this in chapter 4. So the synthesized software, or quarters, will give you a circuit that if A equal to 1, yes, it will give you F equal to B. But if A equal to 0, it will remain the previous F value. So if the previous F value is 0, it will give you 0. If the previous F value is 1, it will give you 1. All right. So it means that this is memory element. Give you the previous value. All right. So you need to be careful when you use if else statement or behavioral modeling. All right, need to make sure that every if you need to have else. Okay, so that will be the synthesis of the circuit. So now let's back to this in front of statement, multiple if statement, case statement. Case statement we will see in chapter 2. All right, with example. Loop. Okay, for repeat. All right, when we write a loop statement in Verilog, these, I don't want to use this example. This is quite confusing. So just ignore this example, yeah, because the example is not accurate actually. So remove these two slides. All right. So for loop, I give you example. Another example. Let's, for example, we have something like this. Always ABC. So begin. So we can use for statement for I. So I you need to in the declaration you need to declare I as an integer, yeah. So before this you need to declare integer I. All right, for I equal to 0 and I, for example, in this case less than 4, yeah. I equal to I plus 1, right? So we do this f square bracket fi equal to a I or b I or c, for example. Okay, and you can have n here. All right. So now we need to synthesize this circuit, yeah. All right. Or we can say that we unroll the loop, yeah, unroll the loop. So what we can do here is we can unroll the loop here to f, yeah, because I is start from 0, so you can have f0 equal to a 0 or b 0 or C. All right, and is it I? Where is it? Okay, is it I less than 4? Yes, because I now is equal to 0, less than 4. So we need to run again. All right, and we increase, before that we need to increase I by 1, because I is equal to I plus 1. All right, so now I is equal to 0 plus 1, we have 1. So now we have another one, which is I 1 F1 A 1 or B 1 or C. C is the same because in our for loop, you see, C is only one C, but A, B, and F is in repeated, because we have I here. And now I is equal to 1. Is it less than 4? Yes, still less than 4. So we plus 1. So we have I equal to 2. So we have F2, A2, or B2, or C. And because 2 is still less than 4, now we have F3, A3, or B3, or C, and we plus 1. Now F is now 4. 4 is not less than 4, then we exit the loop. All right, so we will get these series of statement. Yeah, okay, so if we have this, so we can see create our circuit like this, right? A0. Okay, so if we want to draw the circuit, so A0, so it should be this A0, or with B0, so this is B0, we OR, and we OR again with C, or with C, and we get F0. And we also have A1, or with B1, and we OR with the same C, should be this one, and we have F1. And again you have B2, A2, and A3, B3. All right, you have, later you will have F2, F3, and this circuit is repeated. So by using for loop, you can see that if the structure of the circuit is repeated, it's repeated like this, we can use this kind of statement. So this is repeated 4 times, 4 times. So if want to repeat until 100 times, so the for loop is very good method, right? Instead of writing the code, the statement 100 times, now you write only 1 time, okay, and repeat. The software will repeat for you automatically by using the for loop statement. Yeah, so that is how we infer the circuit from a for loop statement. So whenever you see the for loop statement, first thing you need to do is you unroll the loop. This is called unroll the loop. All right. Okay. Any question? So if no question, so we go to the last part, which is the hierarchical design methodology, where, for example, we want to design a full adder. All right, we will learn full adder in detail in the next chapter, chapter 3. But before that, let's say we have the circuit already, the half adder circuit. So this is half adder, for example. Yeah. So this is the half adder, and we have another half adder, and the connection like this. We know already that this will be a full adder. We use two half adder to create a full adder. All right. And the connection is this, like this. Yeah. Okay. So for example, we have designed already our half adder, and we want to create the full adder from these two half adder, and the connection should be like this. How to do that? And we're in Verilog. Means that we want to reuse our previous code, previous design. All right. So the previous design is, of course, the half adder. Yeah, the half adder. Okay. So this is the way, right? We will use the structural modeling. All right. Remember module instantiation. Yeah, we instantiate the module. All right, the previous module in the new in our new design. So in this case, we need to our new design is called full adder. All right. So this is our new design, and in this design, in the full adder design, we will instantiate this half adder, and the same another one is the same half adder. We instantiate again. All right, and we have the OR gate here. Okay, so this is how we do module. Let's name the module as FA. Yeah, the module name is FA. And what is the port list? So the port list will be A, B, C in, carry out, and sum. Okay, and this is not the port anymore. This will be the wire, internal wire. W1 is internal wire. W2 is internal wire, where W1 is actually connected from the internal half adder, the C, the carry of this half adder connected to this OR gate. Yeah, and W2 is connected from this sum in the half adder connected to the A in this half adder. All right. So our port list will be C in, A, B, sum, and carry. All right. All this signal A, B, C in, carry out, sum. In this case, the name is carry, no out. So just try to remove this. Carry only. Okay. So now our input is C in. Our input is C in, A, and B. And the output is sum and carry. All right. So exactly based on this. So the input is A, B, C in. The output is sum and carry. And now we have internal wire. W1, W2, and W3 are internal wire. So here we need to declare as wire. W1, W2, W3 is the internal wire. And now we call the, or instantiate. This is how we instantiate the module. All right. So the first one is the name of your submodule. In this case, is half adder. The name is half adder. Okay, so the name is actually, this is based on your Verilog code. Do we have Verilog code for half adder? Oh, we don't have. Okay, maybe I write the code for the half adder for you. So how to design the half adder? Anyone know? Let's design together. Alright. Tak ada orang tahu eh? How to design a half adder? Ini this we cross chapter a little bit. This is actually chapter 3 already, but okay, can be introduced here. Let's say we want to design a half adder again. All right. So the half adder is like this. And the adder, for example, we want to have the same name as this one. So let's say the name here, the port name, the input is A, B, the output is C and S. So this name is HA, for example, half adder. So what the half adder do is actually do this. So A plus B, and the product of A plus B is called sum, and the carry, if you have, is called C. All right. And because we have only 2 bits, all right, we can actually get the equation for C and S. All right. So we can have something like this. Yeah. A, B, and here is C and S. Okay. So A, B, because we have only two inputs, so there will be 4 combination only. 4 possibilities. 1, 0, 1, 1. So C, all right, if 0, 0, you plus, of course you have 0, 0. For 0, 1, you plus, of course you have 0, 1. For 1, 0, you plus, of course you have 0, 1. And for 1, 1, you plus, of course you have 1, 0. Right? So now we have this already. So to get the equation is quite straightforward. All right? To get C, so what is C here? You see? Yeah. Okay. If the output is like this, so what is C? Cannot be anything else, right? If 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So this definitely an AND gate. Alright, so C should be equal to A, B. Alright. And what about S? What about S? So S, the output is like this. What gate is this? This is the XOR gate, right? XOR gate. So we have the equation, then we can write the code. We can model our circuit. All right. in Verilog, very easily we can use the data flow modeling. Okay, so how to use the data flow modeling? So let's write the code. So the code is module. We need to module. Okay, module name is HA in our case. The port list, we have A, we have B, we have S and C. All right, based on this, A, B, S, and C. And now we need to have our input. So input will be A and B, and output will be S and C. All right, done. So now we have, us use data flow modeling. So it's assign S equal to what? A XOR B. A XOR B. And the second one is assign C is A. Don't write like this. This is not A and B. In Verilog, A and B, you need to have this, A and B. Now you're done. And module. So this is your half adder, and the circuit is like this. Yeah, and remember this. So we want to use this, use this to design a full adder, and the circuit for that full adder is like this. Okay, so how to do that? So this is how. So we need to, here is instantiate, all right, or call the half HA module that we designed last time, and give it a name. All right, M1 is the first module that in our circuit. We name it M1. So this name can be any name. Yeah, you can name any name. All right. So in this example, the name is M1. All right, and the port. Yeah. So this port we call this style of coding we call positional port connection syntax. Later we will see port connection syntax. This is the same circuit but using a little bit different approach. This we call positional port. What is positional port? Positional port means that the position of this in the bracket here must be exactly the same with what we have done here. All right. So our position is we need to remember our position. The arrangement of the port list is A, B, S, C. All right. Remember A, B, S, C. So in here, okay. So now A, this A, we want to connect to A, the small a, all right, in our previous design. So this is how we write. All right, just write A here. A here. So means that this A is connected to, this A here is automatically connected to the small a here. All right, because in the small a, the first port is, remember, A, B, S, C, right? So the first in the list, our HA is the small a. So this A will be connected to small a, and the next one is B. All right, so this B will be connected to the small b, and yes, correct, because in our HA module, half adder module, the next one in our port list is B, small b. So if we write B here, it will be connected to the small b. And look at the next one, W2. What is W2 in our HA module, which is S, yeah? So W2 in our new circuit should be connected to the S. See here, W2 is connected to S, and W1 is connected to C. So means that here must be W1. Must be W1. Alright. So here, see, we have W1 connected to C. So it should be done for this. Should be done for the first one. Now we want to instantiate or create this one. So how to do? Because we use the same module, same circuit, so again we call that circuit again, the HA circuit here. You see, you have the same circuit here, HA circuit, which is our previous design. And now we name the second one as M2. That's why we have M2 here. Alright, now look at the connection. W2 means that for the second one, the M2, A, small a, is connected to W2. Let's see. Yes, W2 is connected to small a, right? And the next one is Cin. So Cin should be connected to B in HA module. See, Cin is connected to B in HA module. The next one is sum. So sum should be connected to S in this. Yes, sum connected to S here. And the last one will be C connected to W3. And W3 is connected to C. Alright, now we have these two modules already. Alright, this one and this one. Yeah. Now the last one we need to do also, we need to create this one, the OR. And this OR is very easy. Alright, we can use data flow modeling. Alright, the input is W1, W2. W1 and W3, and the output is carry. Alright, you can use structural modeling also can, but in this case use data flow modeling. Assign carry is equal to W1 or W3. Then we have this one. Alright, now done. We have the whole module. Right? Now, let's look at the second way or second method to do the port connection. So this one is named this method is named name port connection syntax. Yeah. So for this one, actually the difference is what in the bracket. Yeah, what in the bracket. So we will see here the declaration part is still the same. The name of HA that we want to call or instantiate is the same HA. The name of the module is the same M1. Now the connection here, instead of position like this, you can actually not in the position also no problem, but we state exactly what this small a is connected to. All right, so the how to do is to put dot a, means that this one, yeah, this one is connected to this a, right? You see, dot a is connected to a, so we tell the compiler exactly that a, the big capital A here, the input here, is connected to this a. All right, dot a and in bracket a, and comma here dot b connected to b. All right, so means that small b is connected to capital B, and the c must be dot c connected to w1, dot s must be connected to w2. So we can see here dot s connected to w2, dot c connected to w1, and the arrangement is doesn't matter now. Here the connection is very important. When you change the arrangement, for example b, you put b here, b a, then the connection is wrong already. All right, means that A is connected to this, B is connected to this. Yeah? But by using this method, doesn't matter, because we tell the compiler exactly this A is connected to this A. All right. Same as the for M2. All right. M2, W2 is connected to A. So you can see very clearly that W2 dot A is connected to W2, dot C is connected to W3, dot S is connected to sum, dot B is connected to Cin. All right. Yeah, exactly. And for the carry should be the same. All right, doesn't matter. Okay, so this will be the two method of port connection, and it is used for hierarchical design methodology, where you call or reuse your previous design to create a bigger design or new design. All right, and we will see that in this code we will see two types of modeling. The first one is using structural modeling, and the second one is using the data flow modeling. All right, and yes, this is chapter 2. Okay, so any question so far before we go to chapter 3? And before that, maybe we take a break for 10 minutes before we go to chapter 3. Any question? And no, sir. No question. There are two possibilities. First is very good, you get everything. Second one is you don't get everything. So which one? Sir, do you record this session? Yes, I definitely recorded. So I will post on YouTube by tomorrow. Yeah. We will have a break for 10 minutes. Yeah, come back at 9:50.